This chapter has to do with differential equations, and to put it simply, I'm going to zoom in. A differential equation is an equation involving derivatives. It has derivatives actually in the equation, which makes them difficult to kind of perceive about what they look like. You don't necessarily need to do that. We're not going to be graphing them. But instead, I'm going to make this a little bigger. Well, we'll just leave it there. Instead, we're talking about something like this. Dy over dx equals x squared. That's an example of a differential equation. Another one would be y prime is equal to dy over dx. That's just an equation of dy dx is equal to dy dx. But if I say y prime is equal to dy dx, we know that at times we've used that to stand in for dy dx. Oops, I want to move that. Let's move that back down here. Just, again, more notational things. Second derivative, we can use the notation d dx of dy dx. And what that means is the derivative of the derivative. And this is commonly written as d squared y over dx squared, which is meant to be a little cutesy play on two d's, d squared y and then two dx's. And by convention, you actually end up writing this as d squared y over dx squared without the parentheses, which looks silly. Or if you want to just make it easy on yourself, just do y double prime, and that's kind of a little bit better. Third derivative, we can kind of talk about y triple prime. That's a thing. Or if you're so inclined, we can say y, and then we'll use a notation of this. And so when see, this doesn't even like having that. When I put the 3 in parentheses, that implies, this implies third root. So that's one. And then if I want to do fourth root, what I can say is this, y with a caret exponent of, we'll see if it likes the double parentheses. There we go. That would be fourth root. So I did that so that you didn't have to read my poor handwriting, as I've recently been told by a certain somebody that it is really poor. But don't worry, we'll get back to writing here in a second. A solution, or what it means to solve a differential equation. Let's get back to a solution to a differential equation. Is an equation itself whose derivative makes the differential equation true. So a solution to a differential equation is yet another equation. The solution is an equation itself. So all of that down, I'm going to kind of go to some actual examples and switch to handwriting. So sorry about that. Number one, show that y equals e to the negative x is a solution to 3y prime plus 4y equals e to the negative x. So if I'm going to show it's a solution, in algebra, whenever we showed something was a solution, we plugged it in and we saw the left side is equal to the right side. So the same thing's going to happen here. I have what y is equal to, but I don't have what y prime is equal to. So I need to take this potential solution and generate its derivative. So I know that this means y prime is equal to negative e to the negative x. And then we're just going to substitute 3 times negative e to the negative x plus 4 times e to the negative x. And I kind of do this with more of a trig proof style, where I'm going to put a little bar here, put equals e to the negative x. That way I'm not actually moving things around, I'm just plugging them in and seeing if the left side is equal to the right side. And at the point that they are, I'm going to circle them. So negative 3e to the negative x plus 4e to the negative x, or e to the negative x. And yes, this is a solution. So let's do another one. Show that x squared plus y squared equals cy is a solution to the differential equation y prime equals 2xy over x squared minus y squared. To get that, to figure that out, if that is a solution, well, let's first kind of start with what I'm actually trying to show. I'm trying to show y prime and 2xy over x squared minus y squared are the same thing. So what I'm going to do is just kind of put that and leave that and just start substituting some things in. Don't get caught up on what you're trying to prove and what you're given. This is the solution that we're trying to use, and we need to plug that in to this somehow. So by plugging that in, I need to take the derivative of my potential solution, which is going to be 2x. We're going to derive this implicitly. 2x plus 2y, y prime equals cy prime. Let's move the y primes to a single side. So 2y, y prime is equal to, or minus cy prime equals negative 2x, or y prime is equal to negative 2x over 2y minus c, which really, if I want to switch this around, is 2x over c minus 2y. So I'm going to take this and substitute it in for y prime, and underneath just write that 2x over c minus 2y. And if you can look at any other substitution that we can make, well, we can make one more. I know that, let's see, I know that c minus 2y, well, there's a cy up here in my potential solution. Let me re-highlight that, this part right here. And I don't quite have that, but I would have that if I multiplied the numerator and denominator of this by a y. This gives me 2xy over cy minus 2y squared. And again, by this thing, cy is equal to x squared plus y squared. So you get 2xy over x squared plus y squared minus 2y squared. And that is the same thing as 2xy over x squared minus y squared, which is the same thing as the right side now, and you're done. Okay, other things you're going to be doing, you're going to be solving. So we're going to solve the differential equation dy dx is equal to x over 1 plus x squared. So we're going to find an equation whose derivative makes this true. And it's going to be subject to an initial condition of y of 0 is equal to 1. That's sort of like that thing where you are trying to find the c value. It's just given that way. So we're going to do this by a process of integration. I might as well integrate the left side and the right side. And what I'm really doing, and this is going to be helpful later, is I'm actually really multiplying both sides by dx, taking this and integrating both the left side and the right side, because the integral of dy is y, and the integral of x over 1 plus x, well, let's pull this down and try to do this integral. I'm just going to erase this and do a u substitution. Oops, that should be an x squared. This is u is equal to 1 plus x squared. Du would be equal to 2x dx. So if I integrate the right side and pull out the 1 over 2, which cancels with the x, I get the integral of 1 over u du, which then becomes 1/2 natural log of 1 plus x squared, which doesn't need to be an absolute value because the value of 1 plus x squared will always be positive, plus c, and this is going to be equal to y, which I kind of carried that down all the way there, and we only need one c value on this whole thing. But I don't even really need to keep the c because I'm going to substitute this in. 1 is equal to 1/2 ln of 1 plus c. ln of 1 is 0, so this means c is equal to 1. And so my final solution is y is equal to 1/2 natural log of 1 plus x squared plus 1. Let's get a better circle. That's my solution. Let's move on to next one. We're going to show that y is equal to 1/2 x squared minus 4 cosine of x plus 2 is a solution to the differential equation y prime is equal to x plus 4 sine x, where y of 0 is equal to negative 2. This is sort of like what we did before, but it's going to be two checks now. The first check, which I'm going to mark as part A, we're going to want to check that y prime and x plus 4 sine x are the same thing. So I'm going to do that as a proof. Y prime, well, we just want to take the derivative of this thing. So the derivative of 1/2 x squared is x, and the derivative of negative 4 cosine x is plus 4 sine x, and that actually matches. So check. Part A is done. Part B of the proof, we're going to want to show that this thing, y of 0 is equal to negative 2, is actually true. So just substitute. Negative 2 is equal to 0 minus 4 cosine of 0 plus 2, or negative 4 plus 2, or negative 2. Check. So we know that that's true, that y of 0 is negative 2, and that the derivatives match. So lastly, we're going to show y is equal to e to the negative cosine of x is a solution to y prime is equal to y sine x at y of pi over 2 equals 1. So same process. We're going to put y prime on one side and y sine x on the other. The derivative of e to the negative cosine x is a chain rule derivative. The derivative of negative cosine is sine, and the derivative of e to something is e to that same something. So e to the negative cosine of x. And if I take this and I substitute that in the right side, I get e to the negative cosine x times sine x, and the two sides are the same. For part B, I'm going to have to see that y of pi over 2 is equal to 1, so y of pi over 2 is the same thing as e to the negative cosine of pi over 2, which is e to the 0, which is 1. And yeah. Okay. Lastly, I know I said that before, there was one more. Determine whether the functions are solutions to y double prime minus y is equal to 0. And I'm going to give you, go ahead. I'm going to give you three of them. F of x is equal to sine x. Then I'm going to give you g of x is equal to 4e to the negative x. And then I'm going to give you y is equal to c e to the negative, or e to the x. So for the first one, we just need to find the first derivative, which is cosine, and the second derivative, which is negative sine x, and substitute. Does negative sine of x minus the sine of x equal 0? That is a no. Even Drake can tell you that one. So,
no, it's
yeah,
most definitely no.
So that's out.
Yeah, no.
No.
No, doesn't work.
Let's go to the second one. Let's find
Yes.
g prime, which chain rule is going to be negative 4e to the negative x, and g double prime of x is equal to 4e to the negative x. So if I do y double prime minus y, that's the same thing minus itself, so that's a yes.
Yes.
That satisfies. And lastly, y prime of c e to the x would be, well, the derivative would be c e to the x, and the second derivative would be c e to the x. So if I take the second derivative minus the original, I get c e to the x minus c e to the x, and that is 0. And that is a yes.